Okay, so there are some problems where I give you some sample statistics and then ask you to complete the ANOVA table. So let's make sure we have, basically I want you to make sure you have all these relationships down. Well, first of all, once we're given the statistics like this, in a sense, I've done a lot of the work for you already in terms of an analysis of variance. I'll start with, I've given you these standard deviations here. Well, remember MSE, the mean squared error, is the average, or at least one way to think of the MSE as the average of the variances for the groups. So if I just take each one of these squared, 2.7 squared, 4.1 squared, and 2.9 squared, and find out what those are, and take the average of them, that's going to be the mean square error. And you're going to put that right here. Then the MSTR, I have the 3 sample means. So first thing I want to do is take those 3 sample means, add those together and divide by 3 to get the average of the means. That would be x bar bar, the mean of the means. Then you have everything you need to calculate mean square treatment. You have the n for each group. So like in the numerator, you have, in the first part of it, NA, that would be 25, times x bar A, that'd be 12.8, minus the average of the means, the x bar bar that you calculated, squared. Then do the same thing for groups B and C. You'll have the numerator of MSTR, which, by the way, that would also be the sum of squares for the treatment, but it would be the numerator for here. So that kind of gets us, that's what I was getting at on this slide, I guess. The average of those 3 means is x bar bar, and then you can use that to compute MSTR. You can get those variances, which I've done here, get the average of those, that's MSE. And then from there, for one thing, once we have those, we know that the ratio of those, MSTR over MSE, that's going to give us the F value. So we've got that. The degrees of freedom for the treatment are k minus 1. There are 3 groups minus 1, so you're going to get a 2 right there. And then for MSE, the degrees of freedom is going to be the total sample size. That's going to be 25 plus 25 plus 25 is 75 minus k. So you're going to have 2, and 75 minus 3 is 72. Again, I'm not going to work these out. I'm just kind of get you on the get the ball rolling on these. Okay, so if you have MSTR and the degrees of freedom, we already knew that sum of squares divided by the degrees of freedom is the mean square. So if you've got the mean square treatment and you have the degrees of freedom of 2, just take MSTR times 2 will give you the sum of squares. If you have MSE and you know that this is 72, then MSE times 72 will give the sum of squares error. Well, if you have the sum of squares treatment and the sum of squares error, add those together and you get the sum of squares total. The eta squared then will be the sum of squares treatment divided by the sum of squares total, and that will tell you the proportion of the total variation, that's SST, the proportion of the total variation that's accounted for by knowing what group we're in. And that's kind of the answer to, I should have just given you one part on that. There was a part there where it asked you about eta squared and how to interpret it and the effect size. It really all comes down to the same thing. So if you answer one of those, you have the other one. You know, the I and double I there for the parts. It's just, if it comes out to be 0.7, that means that of the total variation, the total sum of squares that we had in our original calculation of variance, like if we had all of the data, we've now accounted for 70% of that by knowing which group we're in. That's sort of like on a percentage scale, 0 to 100, how much of an improvement we have in our prediction by knowing which group we're in. Okay, one other, yeah, that's just kind of, I put the degrees of freedom on there. One other thing I wanted to say on the homework is I gave you a website, and actually I gave you direct links to some of it, but if you just come to the main website, it looks like this. And if you go down to the F distribution, we can do, there's 2 things here that I wanted to show you. One is you can get the p-value calculator for an F-test. And I have a direct link in there, but this would be a good website for you to maybe keep an eye on anyway. So let's say that on that problem I had 2 and 72 degrees of freedom. And what I'm just making up this F value now, but let's say that we calculated that MSTR divided by MSC. Let's say that came out to be 6.49. So that's what we had from the table, the degrees of freedom 2 and 72, and we calculated the F value, hit calculate, and there's the p-value, 0.002576. So anyway, here's one approach. If you want to get a p-value and you've got the degrees of freedom and the F value, you can just come in and plug that into that. The other thing is, also under the F distribution, we have a critical value for F calculator. But before I go to that, I just want you to note that this F distribution gets used for a lot of different things, and all of those have F tables. So, you know, the F table and these relationships, sum of squares and mean squares and that, it's not just applicable to what we're going to be able to do in this class, but a whole range of other kinds of problems that you might run across in the future. Well, some of you will run across in the future. Okay, well, I'll put it this way. If any of you are planning on going to grad school, you're going to run across this again in the future, in almost any field. So anyway, in this one I had 2 and 72, my degrees of freedom, and my alpha level is 0.05. Now I'm going to say reject HO if F test is greater. Remember, it's always greater than. My decision rule is going to be reject HO if F test is greater than 3.12. So you can use this instead of using a printed table to get the critical values as well. One other thing I want to show you on this website, which you might be interested in for this homework assignment, is at the very top, you may have noticed that they had something called analysis of variance. One of those tells you that you can calculate a one-way ANOVA from summary data. In other words, it will calculate everything you need, I believe, from, I haven't tried it yet, I just saw it a minute ago and I thought, this would be pretty cool. So in this problem we had sample sizes of 25, 25, and 25, and we had means of 12.8, 9.8, and 14.3, and we had standard deviations of 2.7. Obviously, if you're working a multiple choice or a quiz or something, you're not going to be able to come to this calculator, but for your homework, you can use this to check all of your work. So I just put in the sample size of the means and the standard deviation. I didn't have to get the variance, it's just the standard deviations. And let's see what that gives us. That happens to be the F table. It gives you all the sum of squares, the degrees of freedom, the mean squares, the F test, and the p-value. It doesn't give you the eta squared. That's sort of a it's kind of a thing that's getting new to present in the ANOVA table, becoming more popular over the last few years. But anyway, to do that, you would just take the sum of squares. Let me go ahead and say here, I've said this in the classroom, I'm not sure how much I've emphasized this with the others, but where I'm talking treatment, like sum of squares treatment, mean squares treatment, you will find some other places that call that between, or between groups. You'll find some that just say groups right there. But anyway, so that's your treatment and all of that. Then the within is the same thing as error, and you'll more frequently see that called error, but you'll also frequently see that that's within. If you go back and look at the calculations we did, you realize that when we were computing those sum of squares, when I did the sum of square approach, I was getting the sum of squares within each of the three groups and then add in those to get this sum of squares within. Well, anyway, back to the eta squared, it would be mean square treatment, or between the 262.5 divided by the total of 1042, and what that's got to be somewhere around 0.25. So it looks like about 25% of the total squares that we had originally, that we can reduce that by 25%. So we reduce our error of our prediction, if you want to look at it that way, by 25%. And that's it for this video.